Hi, this is Alex at Knowm Inc. and this video is to help you debug when the memristors are not working as you might expect them to. So first things first, let's change directories to where we have the memristor-discovery jar, and we're going to boot that memristor-discovery program open by typing the following into the console. We're going to specify the v1 flag because we're going to be using the v1 board, and also the test flag because we need to use the board check experiment, which we're going to use to run the programs that we use here in order to classify the chip. So whenever you buy it off of the web store, if it's a tier 1, tier 2, burn and learn, how we determine if a device is good or not is a function of this program right here. So you can go into the source code, you can look at it, and you can see exactly what it is that we use to determine whether a memristor works or it doesn't. So that's the first thing we're going to do, is we're going to repeat the experiment that we do on our end before we ship these things out. First thing, go to Preferences and make sure that the resistance that you have specified for the series resistor is exactly what you have in the board. In this case, it is. I have a 5K resistor in the board. And we have a MEM inline chip. This is the 16-pin chip with memristors in the opposing pins. So we have 8 memristors. We're going to hit this MEM inline chip test. And it's going to go through every single memristor on the chip, and it's writing it with a higher voltage, it's measuring the change in resistance, it's erasing it, it's measuring the change in resistance, and if that conforms, the resistance changes conform to what we have in the code, it passes, and we get a little check mark here. Otherwise, if it doesn't pass, it could fail for a few reasons. 2 of the reasons show up here on this chip. So on the first one, right here, we see that it's failed because it was stuck low. So it started and it was 1.46 kiloohms, which is a pretty low resistance. And after writing it, it went to 1 kiloohms, and then erasing, it dropped even further to 0.95 kiloohms. So this is a misbehaving memristor, and its conductance is very high, its resistance is low, and it's not budging. Okay. Likewise, we have this memristor 7 started and it was 3.7 megaohms, and then we wrote it and it wrote down to 0.148 megaohms, or 148 kiloohms, and then we erased it back up to 1.8 kiloohms. So this is behaving as a memristor. It's just not able to access those much higher conductances as the others do. So we technically failed this one, although there does appear to be actually a memristor here. There's another reason for a device getting stuck high, which is the wire bonds on the chip itself are bad. So, whenever we package these chips, you have the raw silicon die with the bonding pads, and that goes inside the package, and then these little wires go down and they bond onto the bonding pads. And sometimes those bonds are either bad or they fail to stick, so they're kind of welding onto there. So there could be oxide buildup, it could be a bad bond, or it could have come loose. The packaging of these devices has been somewhat problematic from our end. So every now and then, you get a wafer in which the deposition of the materials makes it hard to wire bond, and so you can get basically the chip isn't actually contacting the device. So there's a very high resistance. Doesn't matter how much voltage you apply; it looks like there's no device there. There might actually be a function in memristor, but there's a failed wire bond. There's really nothing that we can do about that. Once it comes back from the packagers, that's it. If it hasn't bonded, then we're kind of out of luck. The other is that the device itself might just have higher variability, and it might be accessing those higher resistance states, and that's just where it likes to be. There's a natural variance in these things, and sometimes you get an outlier. Another is that maybe we just haven't formed it. We haven't driven it hard enough. Whenever we test these chips, we use a 15 kiloohm series resistor, And we try to basically test them just enough to make sure there's memristors there, but not enough to really form them. So it's possible that we can go in and fix this. Okay, so we have device 1 is stuck low and device 7 is stuck high. Now, first let me say that there's only really one reason why a device would be stuck low, which is you have applied a forward applied voltage, or maybe it has been zapped with some static electricity. Whenever these devices are manufactured, they're in their very low conductive or high resistance state. And it takes the application of a voltage in order to drive it into a higher conducting state. So if it's stuck low, it's probably operator error of some sort. Okay, it's been damaged with static, or you've applied higher voltage longer than you should have. Okay, so let's first go. Let's look at this this device 1, which has been stuck low. I've driven this a little too hard, and it is now sort of stuck in this high conducting state. So let's just get a view of this. Let's go to the hysteresis app. First, let me show you device 2, which is, according to the board check experiment, says it was a good device. Notice the 5K here matches the 5K on our board, and we're going to set it to an IV. So we can get that pinched hysteresis loop, and we're going to start it up. And sure enough, okay, device 2, we get our classic memristor hysteresis response right there. Pinched hysteresis, we know it's a memristor. We're going to select 1, and there you go. Okay, so notice that we're in a higher conducting state. So we have, the slope is, it's rather steep. The slope is a function of resistance. So, the steeper the slope, the lower the resistance, or the higher the conductance. And it doesn't appear to be doing anything, right? It's just kind of stuck there. Let me unfreeze the axis or rescale it. What do we have? We have a resistor. So we can do one thing first is we just apply a negative offset and see what happens. Okay, so if we apply a negative offset and then go back to 0 and still nothing. Okay, so what's going on here? It's stuck low. We can't get it unstuck by strong negative DC offset is not doing anything. So let's just try that again. Sure enough, it's still stuck there. Now, ask yourself, why is this? Well, either the device is burned out and it's inoperable, or we're not putting a sufficient voltage across it in order to actually drive that change. So to see this, let's go to let's say the Pulse app. We're going to apply a pulse across this. Let's do a 1 volt pulse. Nice long pulse, 100 microseconds. We have a series resistor 5 there. Okay, so we start that. So we have the voltage here. V1 is the voltage that's being applied. V2 is the voltage that is measured between the memristor and the series resistor. And V1 minus V2 is the voltage drop across the memristor. Okay, so notice down here we were applying a sequence of read pulses to determine what the conductance is, or resistance. So it's reading 1.8 kiloohms. So this is congruent with the board check experiment. And sort of holding steady there. Now recall that we have a 5 kiloohm resistor in the series in the right shunt here. So it's dropping most of the voltage across that series resistor, and we have only 0.25 volts being dropped across the memristor itself. So if we put a negative voltage, so this is trying to drive it in the negative direction, we see here minus 0.25 volts. Now this is insufficient in order to get this memristor unstuck. And we can try to go down to minus 0.25. Let's see if we can do anything. Still, it's just not budging. So there's really only one thing that we can do here, which is we have to lower the resistance of our shunt, or the series resistor. So what we have is a 5K. And what we're going to do, take that out, and we're going to put in a 1K resistor. And let's change this to 1000 like that. And let's try this again. So we have minus 2.5 volts and a 1K. And we can see actually that there's now a much bigger voltage drop. Okay, and we see if we can keep hitting this, if it's going to do anything. And there was a spike here, there's a little noise. So what we're going to do is go to the hysteresis app, and we're just going to see if we can get a hysteresis loop again. So let's take the voltage up to 1, change that to 1K, and IV. Notice we're actually starting to get a little bit of some lobes here. It's not just stuck anymore. So let's do minus 2 volts and see if we can force this thing to reset and go back to 0. Okay, so we're getting a little more movement there. Looks to be kind of inverted. So we're going to take this down to 0. We're going to look at the conductance versus voltage, and we're going to drive this thing all the way down. Minus 2 volts with 1 kilo ohm resistor on there. We can notice the conductance here is now reading 0.65 millisiemens. Let's go back to here to 0.1 volts and up and see if we can increase the conductance. So we can go up to 2.2 millisiemens and go back down. And we are at 0.08. Let's go back to the hysteresis and see if we have response. And what we can see is the lobe starting to open up. We start to actually have a memristor. We've brought it back to life. It was about reducing that series resistance, getting a bigger voltage drop so we can just hammer those ions back across, get the thing unstuck. So the lobes have opened up, and we now have a memristor. Okay, so this is good. We have brought it back from the dead. Notice that the problem here had to do with the circuit that the memristor was embedded in, and sort of the peripheral resistances of the circuit. You got to keep that in mind. It's sometimes memristors, at least these, behave as they should, but it's operator error. So in my case, it was operator error because I drove it into a highly conductive state to begin with, and then when I was trying to get it out, I didn't have a low enough series resistor in order to get the voltage drop to put it back into its initial state. Okay, so let's go to the device 7, which was stuck high. And let's put the 5K resistor back in. Okay, so let's get back to where we were and start up. Okay, notice that the slope is very shallow. Okay, so this is a very high resistance. Let's rescale the axis. Okay, so we have a memristor here, but notice that we're in the microamp current range, and we kind of want to get up, almost to the milliamp for this board with all the RC effects and whatnot. So we're going to see if we can drive this here. So let's add some positive offset and go back to 0. Notice that I have greatly increased the slope of this. So what I did, I had the applying a sine wave, and I just biased everything by a volt. And we can do that. Okay, so I have a 1 volt amplitude sine wave offset by volt. So this is all DC right now. Go back to 0. And now notice that, boom, I've hammered it, and it's now stuck. as a resistor, so I've pushed it towards its sort of maximally conductive state. I can try to reset it by putting a negative offset and then putting it back to 0, and boom, there we have it. Okay, so in this case, we have ourselves a good memristor, but it's a pretty low conductive device. We really, we can get it into a higher conductive state by lowering the series resistor, or we could just use it as is. Now, the reason why this could be problematic is, if other devices are much more conductive than that one, because then there's a variance to it. In this case, it does look like we have brought it in line with the other devices. Let's check out device 1. Again, it looks like we have gotten stuck. And why is that? Well, we put the 5K kilo ohm back in. Notice that we had a perfectly good device when we had a 1K series resistor. Okay, so what's happening in this particular case is that the device has been, the channels have formed to the point where it remembers its high conductive state and it goes there. So we put a voltage and it drops the voltage across the memristor as its conductance increases to the point where the voltage drop is now mostly across a series resistor and it gets into a conductive state and it can't get back out again. Okay, so what we've essentially done is locked out memristor 1, given the series resistor that we have. All the other devices on this chip work nicely and are reversible and work with the 5K. But because we were a little naughty and we drove device 1 to a very highly conductive state, it is now locked out. Okay, so our options here is either to accept the fact that memristor 1 is now locked out and we can use all the other memristors with a 5K series resistor, or we can take that 5K out, we can put the 1K in, and we can use, let's go back to device 1. Okay, I've just changed it to 1K, and notice we have our memristor, and we have all of the other devices work with 1K as well. Okay, so we have this device, looks to be, it's shallow right here, which means that it's still in a sort of high resistive state, and we could bump up the offset here and open up the lobes, and so on and so forth. Okay, so we have taken a chip that has one stuck high, one stuck low, and we've taken the stuck low and we've determined that we have an operable memristor if we used a lower resistance series resistor, and we can use that along with all the other ones so long as we do that. Okay, so the lesson here primarily is don't drive the memristors into highly conductive states, because once you do, that's it. They have to operate at that level and they could get locked out given a high enough series resistor. Well, that concludes this video. Hopefully this was helpful in demystifying some problems you may be experiencing and some of the issues that you'll encounter with memristors that may or may not have anything to do with how you've been treating them. Until next time.